Right, so then as you can see, the first part is about the atomic theories through the history, right? So again, I'm not going into much details. I think you may have discussed about this stuff in chemistry as well, right? You can see now for at the beginning, right? You can see around 400 BC, right? So then Democritus or someone, I think it's a Greek name maybe, was the first person suggested the existence of the atoms, right? So then after that, so then with the time, right? So with a lot of experiments and everything, then whatever the structure, the atoms are made out of this, like that. So then that theory has been developed, right? So then one of the most significant turn, it took a very significant turn, especially once the discovery of the electrons, protons and neutrons were made, right? Now it says in 1803, that means Dalton's model of atom. Dalton found that the different atoms have different masses and can be combined to produce compound molecules. So then after that, the Thomson's model, the Thomson's plum pudding model of the atom, the negative electrons are like scattered through the positive dot, pronounced as dot, right? Right. So then it's like this, right? I think we have a. Have you learned those stuff in chemistry also, no? Right. So he said the atom is kind of like a, let's say, spongy muffin or a plum pudding, right? So sometimes on those muffins, right? So we put some plums on it itself, right? Plums or some fruity fruities. I don't know those names. Okay. Sometimes we put them. So then he said the atom is like that. So like that bun, the muffin, and the electrons are like kind of like those plums placed on it. So then that's a good start. But once the Rutherford's experiment about with the gold foil, familiar with it? What's happening there? Yeah. So then he sent some alpha particles through a very thin gold foil. So then most of the alpha particles went without any change in the path or very slight change, right? So most of it. So fewer particles went something like this, turned away from a different angle, but even fewer ones were like turned completely backwards, right? So then based on this experiment, right? So then he suggested that the atoms are like this. So then most of the space of the atom is empty. So then whatever the remaining stuff is only located within a small center, right? So the center is what we call as the nucleus. So this one, he said, it has to become a positive. It has to be a positive charged one because the alpha particles are positively charged. So when alpha particles are going through this without any deflection, means because it's not even closer to the nucleus of the atom, right? So but once it gets closer to the atom, what will happen? So then it will be turned by a certain angle because the positive and positive repel each other, right? And so then whatever the alpha particles going directly towards this nucleus, it will be repelled completely backwards because of that. Once again, because of the positive repulsion. So from that, this is one of the very important discovery when it comes to the structure of the atom. So then most of the atom space is empty. So the nucleus is confined to a very small region and it has a positive charge, right? So then later on, the idea of generated, like the atom is kind of like a small solar system where the electrons are orbiting around that nucleus, right? Now the belief is right now means after several more experiments, so then current belief is those electrons are not orbiting in like orbits around like just like a planet, right? So they have those what do you call them? PES, sorry? Yeah, so then they have not just one orbit, a range of space where the electrons can exist, right? So then I think it was also mentioned somewhere in the note. Is it? Yeah, later it's there, right? So quantum mechanical model of an atom structure. So it says atom has regions of rounding nucleus in which there is a high probability of finding electrons, and the shapes of these probability clouds represent what the currently referred to as the electron orbitals. That was mentioned in page 77 later, right? So then that is the basic idea of the atomic structure. Okay, so I don't want you to write about these things, right? So again, since you have learned about these things in chemistry, and the Rutherford experiment also explained in page 75. You can refer to that. Right? So conclusions and observations. Right. So then later on, right, so then it says here on page 76, the Chadwick's discovery of the neutron, but you can see it's labeled with the red sign on the left. It says you don't have to know about this in the exam, it's just there for your understanding. So it's that experiment describing how the neutron was discovered. Once again, you have to know about that one either. Right? Right. But when it comes to the neutrons, right, so we need something. Right. Again, we will be coming back to these ones later in a separate topic as well. Right? Now, when it comes to the nucleus, what do you have inside the nucleus mainly? General idea is protons and neutrons, right? So then we know the protons have what kind of charge? Positive charge. And the neutron? No charge. It's neutral. Right. So then how do these protons, which are positively charged, existing inside the atom or the nucleus, when they are repelling each other? Right? It's like several enemies were placed inside the room, right? And let's say you are not friends, assume you are enemies, you hate each other, you are waiting to slit each other's throats, right? Right? So then how do you stay inside the class? Because I made you to stay. Right? No one is going in, you have to stay inside the class until the end of the class, right? So then if you want to keep those protons, you have to do something like that. Stay. No go. Right? So you can't go out. So then the protons, technically speaking, right, we know when two things are having so similar charges, if they keep them together, they have to repel each other, right? So but in atoms there are more than one protons, right? So in that periodic table, if you take like at least carbon has 6 protons in it, so then they should be repelling each other, right? So they like that. So when you go along this periodic table, more protons are there, means more repulsion forces are there. So then how do they stay there? It's because of these neutrons, right? So neutron has some sort of bonding forces between the protons and the neutrons. It's like I'm keeping those enemies together inside the class, right? So then that force between the protons and neutrons, we call it as a strong nuclear force. Right. So now, if you, I don't know whether you are going to carry in the physics field, right? So if you, those who are interested in physics, right, then this is a very interesting topic for those people, right? So later we will be mentioning again somewhere in this chapter itself, right? So we will be discussing there are 4 main types of forces in the universe, right? One is something that you know, yes, you learn gravity or gravitational force. Second one also you have learned. Sorry? It's known as electromagnetic forces, right? Especially the electrostatic forces, right? So the forces between positive and negative charges. Okay. Now the magnetic forces are not considered as main types of forces. So then this is the next one, strong nuclear forces, and there is another one called weak nuclear forces. So then those forces are considered as the base fundamentals of the kind of like a fundamental of the entire physics knowledge, right? So then most of the physics is developed on about the knowledge about those forces, right? So then this is a very important force. So that's the strong nuclear force between protons and neutrons. That is what held in the nucleus together, right? Now you know, and I can't remember the values exactly, right? So if you take like carbon we have about 6 to it, right? So then what is this 6 means? Number of proton, we call it as atomic number or the proton number. So that means there are 6 protons are there, and this one is mass number, right? So the mass number means neutrons plus protons. So then 6 protons are there, so the neutrons plus protons is 12, so then number of neutrons also has to be 6, right? But later we will have atoms like, okay, something 90, 250 or something, right? Now this is hypothetical one. Okay, there's example in your textbook, you use that. So radium 88 to 26. Right. So here we have 88 protons, and how many neutrons are there? 8, 3, 1, 3, 8, is it? Something like that. Right. You can say when there is less number of protons, the number of neutrons are almost same. Right? But when the number of protons are getting increased inside the nucleus, so then what will happen? The number of neutrons required is also going to be higher. Why is that? Why do we need more neutrons? Now there's only 3 of you, right? So then the enemies, 3 enemies, I can manage you 3. But if there are like 88 enemies together, will I be able to manage? No. So then I need some help, right? So then when there's more repulsion force, when there's 88 protons repelling each other, so then if you have exactly 88 neutrons, so then that nuclear force between the protons and neutrons may not be able to keep it together. So therefore, it requires more neutrons, giving us more strong nuclear forces. Okay, so that is why when you see, if you go to the lower sections of that periodic table, you will have more neutrons than protons. Okay, so then that neutrons are playing a very important role when it comes to the nature or the structure of the atom. Okay, right. So then this is also you have to know, right? So this number, proton number, the mass number, right? Again, you have learned those things in like basic chemistry, right? So maybe on the very first day of the chemistry lessons. So therefore, again, we are not going to write anything about that. Do you need to write? I don't think so, right? Right. So then, okay. So that's the basic part about the first lesson, right? So then we can go for the next part. Right? So we are only discussing the things that we need to know, right? Right. So then if you go to the next part, that is on page 78, it says electrons from atoms. Right. So we'll read through this one, right? So free conduction electrons in metals need a particular amount of energy if they are to escape from the surface of a metal. The energy can be supplied by a beam of photons as seen in the photoelectric effect. The electrons can also gain enough energy through heating the metal. So the release of electrons from the surface of a metal as it is heated is known as thermionic emission. Right. Now the first part, that photoelectric effect, we have learned during the AS section. So that means when the energy from a photon reaches a metal surface, the electrons can absorb that energy photon and can relieve the metal surface, right? So then another way of releasing electron is what's mentioned there, the thermionic emission, right? So as it says, the thermal heat energy, right? So by supplying thermal energy, we can make the electrons to be released, right? Now I think you have learned about generation in X-ray in chemistry. Have you? No? Okay. Right. Now you know X-rays, right? So the ones they use in hospitals, right? So then that X-rays are using generated using electrons actually, right? So then electrons will be released using this thermionic emission, right? So inside some sort of a tube, right? So then those electrons will be decelerated using an electrical field. So as they decelerated, so the initial kinetic energy of the electron has to go somewhere else. So then that energy is what converted into the X-ray, right? So the energy will be enough to convert it. The energy is in the range of the X-ray range. So therefore that energy will be giving us the X-ray. We need to do our experiments and everything, right? So that's what mentioned there. And after that, learning tip, it says if when they escape, these electrons are in an electric field, they will be accelerated by the field, moving in the positive direction, and the kinetic energy they gain will depend on the PD that they move through according to the equation Ek equals Ev, right? So then that also you have somewhat basic idea, right? So that means if that electron is released from a certain surface, right? Okay, so there's a positive charge here, that means it's like a negatively charged plate or something. So then because of this positive negative force, potentials, right? So then it will be accelerated towards this direction, right? So then as a result, what will happen? We know with this equation, potential difference is equal to energy divided by charge. So then charge is equal, sorry, energy is equal to potential times charge. Okay, potential times charge. So then these are electrons, so then the electrons charge is E, and if you take it as E times V, so we can get the energy gained by these particles. Right? Now if the electric field is in the same direction as the motion, so then energy will be gained. Right? So then if the electric field is in the opposite direction to the motion, energy will be lost from the electrons. Right? And so then that's what mentioned there. After that, worked example is there to show how to apply this equation. And again, once again, I'm not discussing through that one which details. So the next part is important, but using thermionic emission to produce electrons and applying an electric field to accelerate them, we can generate a beam of fast-moving electrons known as a cathode ray. If this beam of electrons passes through a further electric field or magnetic field, then the force produced from the beam of the electrons will cause it to deflect. So if a fast moving electron hits a screen that is painted with a particular chemical, the screen will fluoresce, that means like glow, that means it will emit light. These are the principles by which the cathode ray oscilloscope operates. The electron beam in a CRO is moved left, right and up and down by passing a beam through horizontal and vertical electric fields. These are generated by electrical plates so that the strength and direction can be altered. The point on the screen which is emitting the light can be changed. Point on the screen which is emitting the light can be changed quickly and easily. Right? So then, have you heard about that instrument? Cathode ray oscilloscope? Have you seen it? No. Yes. Where do we use this instrument? So cathode ray oscilloscope is one with the screen, right? So then there are a lot of button switches are there, right? Now if you want to observe some waves, the pattern of the wave, right? So we can observe using this kind of cathode ray oscilloscope, right? Now for example, I don't know whether you have seen it or not, right? Now if let's say if you are observing a sound wave, right? So the sound wave if you want to observe, you need to connect this cathode ray oscilloscope to a microscope. So then microscope will mic will convert that sound wave into an electrical signal, and the electrical signal can be waved on this screen, something like that, right? So then that one is used to observe the wave behavior, right? So then using that kind of figure we can find out the frequencies, time periods, right? So then amplitudes, energies, that ones we can observe, right? So then the working principle of that cathode ray oscilloscope is what mentioned there, right? Once again, it's also they are not. We don't need to go into details, right? So therefore, I'm not giving you a note on this, but this part somewhat important, right? You have to know what is meant by a cathode ray oscilloscope and everything, right? So then, after the next part, so if you need to write down something. Next one, it says the electron probe. So electron beams fired at a crystal will produce a scattering pattern that can tell us about the structure of the crystal. Davison and Germer loved that an electron beam can produce a diffraction pattern. This was different to the pattern found by Geiger and Marsden in Rutherford alpha scattering experiments. Those two provided the experimental evidence to prove a theory that had been suggested 3 years earlier by French physicist de Broglie. The light could be shown to behave as a wave sometimes and at other times as a particle. He hypothesized that this might also be the case for the things which were traditionally thought to be particles. So then de Broglie had proposed that the wavelength particle could be calculated from the momentum using the expression. So that's also something that we discussed during the ACE section, right? So if the waves, the light can show diffraction patterns, the particles also showing the diffraction patterns. So particles means electrons. So then their diffraction if they are behaving as if they are showing diffraction pattern, which is a wave behavior, so then they should have wavelength as well. So then that wavelength is what we are given by that equation, Planck's constant divided by the momentum. Okay. So then the Davison's-Germer experiment proved that the diffraction pattern obtained when a cathode ray hit a crystal could only be produced if the electrons in the beam had a wavelength that was the de Broglie wavelength. Because of this experiment confirmation, Louis de Broglie was awarded the Nobel Prize. Okay, and so we don't mind the Nobel Prize, right? Is it clear what it was saying there up to this point? Okay, right? Okay, that's not that difficult, right? So it's just some things that we already knew, right? And de Broglie wavelengths, everything can be calculated from those kind of equation. Again, we are not doing that now because this is not the most important part. The one is coming. The next part is the one we need to discuss, right? The next part means after the page 79, right? So we'll go through the page 79 also because it's there. So worked example is there, practical skill is there to investigate electron diffraction, which we can't do. We don't have that kind of technology. So the idea of electrons acting as waves has enabled scientists to study the structure of crystals the same way they do in X-ray crystallography. When waves pass through a gap which is about the same size as the wavelength, they are diffracted. In other words, they spread out. The degree of diffraction spreading depends on the ratio of the size of the gap to the wavelength of the wave. If a beam of electron is aimed at a crystal, the gaps between the atoms in the crystal can act as a diffraction grating, and the electron waves produce a diffraction pattern on a screen. Measuring the pattern allows the space in between atoms to be calculated. Right. Now, as the electrons can diffract when they pass in through gaps, right? So then that technology is used in to observe the structure of that kind of whatever the crystal it passes through, right? Actually, this is the technology they use to generate the microscope, the electron microscope as well, right? So instead of using that was we had about the microscope, we had a brief small description about the microscope as well. Not how it works in details and anything, right? So instead of light lenses, we will be using magnetic and electrical fields to diffract change the direction of the electron beams. So and as they move through those kind of crystal structures, so depends on the size of the gap, right? So amount of diffraction depends on, right? So now that one we discussed it during the waves as well, right? So if there are gaps in the size of the wavelength, so then the diffraction happens better. So if they diffract better means the electrons are moving through large regions, so then it will provide us with a larger more information about whatever the structure that we were observing there, right? So then that's what mentioned there, and next part is there. Electron diffraction and alpha particle scattering both show the idea that we can study the structure of matter by probing it with beams of high energy particles. The more details of the structure to be investigated as the higher energy beam of particles needed to be. This means that the very high energies are needed to investigate the structure of neutrons, as they are very, very small, and accelerating larger and larger particles to higher and higher energies have been the aim of particle physicists ever since Thomson discovered the electrons in 1897. So then here we are in the point we want to go for the next section, right? Right. So then if the particles, electrons, can move with a certain energy, right? So it produces more energies, that means more details, right? So then this is the technology. Now, let's say the technology has been developed to observe, that means to increase the energy, that means the speed of the electrons as they move, right? So then that's what we are going to discuss next, right? So we'll go to the next part as well, right? Again, you can just read the note, okay? So previous part, I'm not giving you any note there, right? And that's not difficult, okay? The ones we were discussing up to this point. So then actually the next part is the one I consider to be the real lesson there, right? So about the particles accelerators, right? Do you learn about subatomic particles in chemistry?
In physics.
Physics you did not, right? Okay, but in chemistry no, right? I don't think so, right? Yeah, generally it's considered as a physics lesson, right? Now, when it comes to the particles, right? So now, for longer time, right? So then it says about 400 BC or something, right? So the structure of the existence of the atoms was suggested, right? So then with the time passing, so as we were discussing, right? So then atom we for a longer period, everybody believed atom is the smallest thing that every matter is made out of. So then later they discovered that even the atom has even smaller particles, protons, neutrons, and electrons, right? But now we know electrons, especially protons and neutrons are not even the smallest particle. So then there are even smaller particles are there, right? So then those smaller particles, we call them as subatomic particles. So then the discovery of those subatomic particles, right? So then they were proved, the existence of that subatomic particles were determined using those something called particle accelerators, right? Now, as the name suggests, what does these things do is accelerating the particles, right? Particles means such as electrons. Okay, so then here what we do is, right, so we want to increase the speed of electron or any other particles which is moving, right, to very high values. So then using general apparatus, right, that we have, right, so electrical fields, plates or anything, right, we can only accelerate the electrons or any particle to only a very small amount of velocities or a small amount of speeds, right? But to increase the speed up to a very high value, right, so then we use something called the kind of particle accelerators. Okay, and so once again we'll go through the note, then we'll discuss in details. To investigate the internal structure of particle like nucleons, protons and neutrons, scientists collide them with other particles at very high speeds. It is necessary to use high energy particles because at lower energies the particles just bounce off each other, keeping their internal structure secret. If we can collide the particles together hard enough, they will disintegrate and show their structure. In most cases, additional particles are created from the energy of the collision. Sometimes these extra particles uncover or confirm the other new physics. So then challenges for the scientists has been to accelerate particles to high speeds. So then charged particles can be accelerated in straight lines using electrical fields in their direction changed along the curved path by a magnetic field. Right. Now, even when we were smaller, right, so if you are given a toy, right, so not only small, right, so now we have that curiosity, you know, if we are given something, what is inside this thing? Right. So that curiosity is there, right? So then what do you do? The children, right, smaller ones, even us sometimes, open and see. If it cannot be open, so then we have to break whatever the object to see the inside, right? So then to reveal the secrets of the atoms, so we have to open them up. Can we cut with a knife the atoms? No, right? It's too small. So then how do we open up those atoms? Is by making them collide with another particle. One particle colliding with another, right? So that means like a nucleus of atom colliding with a high-speed electron, right? Now to do this, right, so if that splitting or the opening or the atom to break into pieces, right? So the speeds of the electron or the moving particle has to be really high, right? So if it's going like 100 meters per second, that will still not work, right? So it should be really large, right? So then that kind of very large velocities we can achieve from a particle accelerator, right? Now this is a very complicated topic, right? So then actually it's dialed down for us, simplified for us, right? So then particle accelerator, right? So they are using electrical fields and magnetic fields to increase the speed. Especially the electrical fields are used to increase the speed, right? And sometimes we have the particle accelerators where the particles are going in circular path, right? So then those are known as circular accelerators. So then in those kind of things we use the magnetic fields. Okay? Right. before discussing about the particle accelerators, we'll write a small note about this, the general idea. You can write the topic as particle accelerators. To investigate the structure of an particle, they will be collided with other high speed particles. To reach these high speeds, those particles must be accelerated. Accelerated using particle accelerators. Now, when it comes to this particle accelerator, you can see the first part is the linear accelerators. Right? So, linear accelerator. The basic structure of the linear accelerators, you can see it's given in your textbook. Right? So, you can see there are several tubes are there. Right? So, then you can see the tubes are connected to an alternating power supply. Right? So, each alternate, you can see the one, let's say, set up like this, this tube. You can see these two will be connected to the same positive or negative terminal, right? The other one is connected with the opposite terminal. Okay, so then if there is a next one, so then the next one also connected to this other one. So then this is going like this. Alternating power supply is here, right? So then you can see alternating power supply is this is positive, this is negative. So if this is positive, then this is positive, and once again this one also positive. So then if this is negative, this will be negative, right? So then what happens? This alternating supply, so that means positive, negative. That negativity is changing, polarity is changing. So then this one becomes negative, positive, right? So then that changing is a must. Okay, right. So this is what happens, right? Now initially this will be negative, right? Let's say the electron, we send an electron into this, right? So how do we get the electron? Is maybe using photoelectric effect, or most of the time it will be using thermionic emission. That means when you heat some metals, they will release electrons. So then those electrons will be sent into this one, right? Now, as the electron is inside this one, let's say electron is here, right? What is happening? So the electron is inside a negative field, right? So the negative and negative, electron also negative, they repel each other. So then what will happen? This electron will be kicked out of this thing, right? And as it being repelled by this tube, here we have positive tube. So then what will happen? Electron is repelled by this one. Since this is positive, so then the electron will be attracted towards this one. Okay, so then as it acts, so this repulsion and attraction, they are forces. Right, so then we know if there is a force acting on an object, so then they will be accelerated. So then as it goes from there to there, it's going to be accelerated. Right? Right. Once it's inside this tube, now what will happen? This alternating supply. Once this electron is inside this tube, so then this tube is going to be negative now. Then what happens? This one is once again repelled from this one. So then if this is negative now, this will be positive. So then the electron will be repelled by this one and it will be attracted towards this one. So once again using another force, so then it will be keep on accelerating towards this side. So once the electron enters this thing, so then this one again become negative. So the negative tube will repel the electron and this positive one will be attracting the electron. So then it will be keep on accelerating like this. Understood or no? That process. Clear? Right? So this one they ask in papers. How do the electrons are accelerated using this kind of linear accelerator? Understood? Right? Now this is not just very short with now this setup is not only for like this kind of from this goes for like several kilometers, right? I think somewhere it was mentioned on that last line in that same paragraph, linear accelerator. Using this principle, the 3.2 kilometers stand for linear acceleration USA can accelerate electron to an energy of 50 giga electron volts. Right? So then that this kind of tube setup is there for a length of 3.2 kilometers. Right? Now comparative to the electron, so that's a very long distance, right? Size of the electron. So that means as it passes through entire that 3.2 kilometer alternating tubes like this, so at the end it will reach a very high velocity. Understood? It will be reaching very high velocity. So then if wherever this last tube is here, right? So this is the last tube. As the electron is coming out of this, so then there will be another particle waiting here, right, to collide with it. Right? So then very high speed electron collides with this particle, and as a result it will be making new particles. It will be showing what is inside it. So then using calculations, whatever the scanners we have, right, so they are detecting the velocities, masses of those particles, radius of curvatures, everything. What from the setup they have it here where the collision is occurred. Understood? And so then that is the techniques that you use in a linear accelerator. Are we clear? Okay. Okay. Right. So first we'll read through that note as well. Right. So then linear accelerators, one of the simplest ways to produce energy high enough for this particle collision is to accelerate a beam of charged particles along a straight path. However, the maximum achievable potential difference limits them. To overcome this problem, the particles are accelerated in stages. They are repeatedly accelerated through the maximum potential difference, making the particles energy very high. Using this principle, 3.2 kilometers stand for linear accelerator kinetics electron. Okay, right. So, did you know? After that part, it says if the particles to be accelerated by the linear accelerator are electrons, they are generated by a electrostatic machine like a Van de Graaff generator and then put it into a machine. So once inside the cylinder, electron move in a straight line. Electrodes are equally attracting in all direction. The alternating voltage supply is made to change the electrons reach the middle of the tube, so it becomes negative. So then every time the electron reach the middle of those tubes, so then the polarity will be changed. So positive become negative. So then it will repel to the opposite direction, right? So that's what so it becomes negative. This repels the electrons out of end of tube A and towards tube B, which now has the positive potential. They are accelerated towards it, and the whole process repeats as they pass through tube B and then accelerated on towards tube C. This carries on until the electrons reach the end of the line, at which point they emerge to collide with the target. Okay, clear? Right. You can see very interesting. You have to know this thing, okay? So then we'll mention about this one, linear accelerator. So after that, you draw that figure that they have given on your textbook. Just copy the figure. A linear accelerator consists a set of tubes connected to an connected to an alternating power supply or voltage supply, alternating voltage supply. The adjacent tubes have opposite signs of volt. What do you call that? Polarity, no? Can you call it polarity? Written charge. Opposite charge. You can say plus and minus voltage, opposite voltages or opposite voltages. You can brackets mention plus and minus alternatively. Next point, right? If an electron enters the first tube, first the tube will be positively charged. To attract the electron. And when the electron reaches the middle of the tube, it becomes negative. This repels the electron from the first tube and will be attracted by the positively charged second tube. Or just positive second tube. So, right, these electric fields continue to accelerate the electrons through all the tubes using the same process. Okay. Right, question. Why do these tubes get longer as it goes on? Speed is getting increasing, no? Right? Speed gets higher. So therefore we need the alternating supply is the same supply, so it changes plus minus signs with the same frequency, right? If it is changing in every half second, so then it is always every half second, right? So then during that half second, the electron should reach this point, middle of the point, right? So initially it will be positive, so then once it reaches the middle only, it should be turned into negative. Then only it will be repelled to this side, otherwise it will be going backwards, isn't it? Right? So therefore once it reaches here, that means since the speed is increasing therefore, so then the distance, it has to move a longer distance before it reaching the center of the path as the speed increases. So that's why these tubes are getting longer and longer. Okay, so then these things they can ask you in a question like why those tubes increasing the length, that can be asked, right? So then they had asked even in recent papers 23 or 4, right? So they given this setup and there was a question we do later. Right, so why what is that process, how the electrons are being accelerated through this setup? They have asked those things. Okay, clear? So then this is basically the idea of a linear particle accelerator. It's not that difficult, right? So you just have to know how it is being accelerated by changing that plus minus voltage signs. Okay, right. Right. So then last paragraph there, right? In order to keep the accelerating particles that are moving faster and faster, the acceleration tubes must be made longer and longer as the particles travel through each successive one at a higher speed. The time between the potential different flips is fixed as the alternating voltage has uniform frequency of a few gigahertz. Using this type of accelerator is limited by how long you can afford to build it. So the whole structure must be in the vacuum so that the particles do not collide with the air atoms, and it must be perfectly straight. That's idea is clear, right? So then we can't build up forever, right? So we can't build this thing around the entire Earth, right? So it's too much, right? So therefore we have only limited length, right? So it says it's only the 3.2 kilometer one in America is still the longest one, but they are still trying to make a 15 kilometer one. I think they must be still doing it in Japan, right? So then that's it about this, and that vacuum thing, right? So that's also important, right? So then that also they can ask why do we have to vacuum the insides of these tubes to avoid the electrons from colliding with the gas particles, right? If there are gas particles, so as the electrons move through it, so then obviously they will collide with the gas atoms. So then this will maybe stop the motion of the electrons, right? So that's also possible. Okay, right, so then mention those 2 points there. As the speed increases, length of each tube has to be increased because it travels longer distance before the potential difference is flipped. Insides of these tubes must be vacuumed to prevent the electrons from colliding with the air particles. Right, you know about Einstein, right? What comes to your mind when you hear the word Einstein? Yes? Anything? Huh? Relativity, okay. So, anything else? Yeah, that's what I was expecting. Right? Yeah. So, this equation, mc squared, have you heard? What is E? E means energy, M as C is speed of light. Right? So, then he said, general idea is we can't create energies. No? In energy conservation, we said we can't create energy, but actually, we can convert a mass into energy. Right? It's not exactly creating energy, it's just converting a mass into energy only. Right? So then that relationship, if you can convert the mass into energy, so that relationship is given by this equation. Right? It's actually true, right? So now this mass is converted into energy. Right? So we'll be later in this chapter itself, a separate chapter. Right? So somewhere we discuss about the nuclear reactions. Separate chapter. Yeah. Nuclear reaction, right? You know nuclear power plants, right? Even though we don't have it in Sri Lanka, as well in different countries there are nuclear power plants. So then, in those things, using nuclear reactions, then we generate electricity, right? So then, in those kind of situations, during those nuclear reaction, a small amount of mass disappears, right? Before the reaction and after the reaction, so the masses are not the same. Small amount of mass will be disappeared. So then, what happens to that mass? So it is not converted into energy in a nuclear power plant. Right? So then that relationship is what given by this equation, and you know c is the speed of light, that is 3 into 10 to the power 8. So then here we have square, that means 10 to the power 16 it becomes. So then even very small mass can provide very large amount of energy. That's what given by this E equals mc equation, right? So there are t-shirts saying this equation. You have seen? I have seen a lot of t-shirts. E equals mc. I don't know whether those people who are wearing knows about that equation or not, right? Anyway, right. So then this is what said by Einstein. So then Einstein actually has discussed a lot of things related to this particle physics as well, right? Now even in the photoelectric effect we discussed, right? So then that's also theory. I mean that information that the ones we discussed, some stuff that we discussed related to photoelectric effects also provided by Einstein himself, right? Now he has discussed about this particle accelerators, right? So then about particle physics as well, right? Right. So one other very important thing that Einstein has said among the lot of things that he has mentioned is that nothing can reach the speed of light. No particle, no object can travel in the speed of light. That's what he said, right? Now, so using particle accelerators, right? So then when the speed is increasing, theoretically speaking, at some point the particle should be able to reach the speed of light, right? But actually that's not happening, right? So then that's what led to believe this as Einstein's theory must be correct, right? So still scientists are working on those stuff, right? So the current idea is when the particles are getting at least closer to that speed of light, right? So they can get closer to the speed of light, but they are not reaching that speed of light either, right? So then this situation we call it as the relativistic effect, right? So there what is happening is mentioned in the next part, right? Right, you read through that one, so then we will discuss in details. So was Einstein right in page 87? So one of Einstein's claim in his theory of special relativity is that nothing can accelerate beyond the speed of light. This means that the particles in particle in accelerators must have problem when they are already traveling closer to the speed of light and then pass through a potential difference which should accelerate beyond it. Right? Now, it's the speed of light. If it is very closer to the speed of light, right? If it is continue to accelerate, so that at some point it should go even beyond the speed of light, no? Right? So let's see what happens. In 1964, someone demonstrated that at very high speeds, particles deviated from the equation E equals mc, the kinetic energy equals QE, right? Now in those particle accelerators, we had electrical field, potential difference. So then potential difference, whatever the energy supplied by that potential difference is what causing the kinetic energy to be increased, right? So earlier also we mentioned, right? So if we have electron, right, if it is passing through negative and positive potential difference of V, so the energy gained by this potential difference due to, by the electron is EV, right? So energy gain means it's increasing the speed, so that means this energy will be converted into kinetic energy, right? So if you continue to go like this, so then the speed of light should be very high, reaching the speed of light. But the thing is, as it says, it's not going in that way. It never accelerates beyond the speed of light, right? So then after that it says, by measuring the actual speed of the electrons accelerated from the Van de Graaff generator and then determining the actual kinetic energy by colliding them with a target and measuring the heat generated, Bertozzi, this, right, so was able to show that the energy added by the accelerating PD started to become more than the amount expected from half mv square. Understood or not? Right. Again, last part, measuring the heat generated, Bertozzi was able to show that the energy added by the accelerating PD started to become more than the amount expected from half mv square. Okay, we'll read through the next part as well. This demonstration shows that whilst the kinetic energy and the momentum of the particles can continue to increase without limit, their speed does not, right? Now what we discussed was speed cannot reach the speed of light, right? But still the electrons, as they accelerated through this accelerator, we provide the energy, right? So kinetic, that means we are supplying energy, means the kinetic energy has to be increased, but the speed cannot go beyond the speed of light either. So then what is the other option we have? The mass to be increased, right? So then the moment the particles gaining the kinetic energy, yes, right? So once it reaches the speed of light, now up to this point, right, I can see it's complicated, yes. It will take several readings of this thing to understand it fully, right? Okay. Let's say the speed of this electron is about 98% of the speed of light, right? So when it reaches the end of one tunnel, right? Now we have another tunnel, another set of tunnels there, right? Now once it goes from there to there, it's continue to accelerating, right? So then technically speaking, because of this potential difference, now this is minus, this is positive, so then there's a potential difference. So then that potential difference is accelerating the particle, means this electron should gain more energy, right? It will be given energy, so electron is gaining the energy, but the speed not increasing beyond that point. So then what is the only other option? Only option we have is to increase the mass, right? So then that's the thing happening, right? So then energy is continuously supplied, but the speed does not increase, but the energy is increasing, means the mass of the particles are getting increased, right? So then initially, normal situation, right? If you are running from here after the class to home or something like that, our mass does not increase, our mass decreases. Right? We have burning the factory and everything, right? But these ones, if you are running too fast, not running, the particles are moving too fast, right? That will happen because if we happen to move very closer to the speed of light by somehow, right? Let's say, right? So if you happen to move like more than very closer to the speed of light, so you won't go beyond the speed of light, but if you are continuous to supply energy, what will happen is your mass will be increasing. Understood? Right? So then this situation is what we call as that relativistic effect. Somewhere it's mentioned in your note. The relativistic effect. Okay, I think it's there somewhere, right? Maybe in the last line, right? So then again, that last paragraph once again. So then this demonstration showed that whilst the kinetic energy and the moment of the particles can continue to increase without limit, their speed does not. This can only happen if the mass of a particle seemingly increases with its speed. So then this apparent mass increase becomes significant at speed approaching the light speed, known as the relativistic speeds, right? Relativistic speed. So then this situation is what we call as the relativistic speed, right? Okay, where is that mass is coming from? Answer is there. Equation. right? Now equation is originally defined for energy is converted in, so mass is converted into energy, but here what will happen is when the speed of light is going to achieve, right? So if you continue to supply energy, so then that energy will be converted into the mass, right? So for those who are interested in physics, this is a very interesting area, right? This is the only thing that I'm interested in this lesson. Other than that, it's a boring story, right? The scenario is interesting. Okay, what is happening is interesting, but reading and teaching kind of boring. Right, is this understood? What is meant by relativistic speed? So simply that means even if you run, now normally we've been running with low sound masses, but if you try to run at the speed of light, if you can run at the speed of light, so then you will gain mass, right? So therefore don't run it, try to run at the speed of light, okay? Right, like this relativistic effect, right, relativistic effect. When particles are accelerated, to a potential difference of V, they gain energy equal to QV. Q is the charge, V is the potential difference. And this will be converted into the kinetic energy. Separate, right? Half mv square equals qv. So then use to we'll write half mu square equals 2v square. Little bit complicate, may complicate you. And half mu is the speed, v is the potential difference. And better to use capital V there. B. Separate, right? If the particles are continue to accelerate, their velocity should go beyond speed of light. But when the speed reaches the speed of light, when the speed of the particle reaches the speed of light, energy will be converted into mass Therefore, the mass increases. But the speed won't go beyond the speed of light. Speed will not go beyond speed of light. This is called relativistic effect. The speeds where mass significantly increases, where mass increases are known as relativistic speeds. Are known as relativistic speeds. Right, is it understood what is meant by relativistic speed? Clear? Right. Right, so then just keep these things in mind, right? So then before we go to the next one, right? Right, so then so far we were discussing about the linear accelerator, so where the particle speed will be increased step by step by using a set of tunnels, right? So in each tunnel we will have a change in plus minus voltage, right? So then it will be continuously increasing the velocity of the particle, right? So as the velocity of the speed increases near the speed of light, so the mass increases where the speed won't go beyond the speed of light, even though we continuously supply the energy. Okay, right. So the next one is about the circular accelerators, right? Now, if you can remember magnetic fields. So we learned in magnetic fields, if we have a magnetic field into a plane like this, if a charged particle enters this one, let's say it's a positively charged particle, so then according to Fleming's left hand rule, this positive charged particle, so then direction of the current is same as the velocity, this way the field is in the plane, so then there's upward force. So then because of this force that will happen, this particle will be moving in a circular path. Okay, so this is going in a circular path. So then if the electron enters, it will be going in a downward path, downward circular path, right? So then this, there are relationship we can get from. So then charge is dQV, this is equal to centripetal force mv squared over r. From that we can set up the radius of this path as mv divided by vq. Okay, right. So using this kind of magnetic field, right? So instead of sending the electrons in a linear path like we discussed before, now the problem there was, as we discussed, there also, right? So the length, we can't have like infinitely long line of path, right? So we can't have a continuous longer path throughout the world or anywhere, right? So it has to be limited, length has to be limited due to environmental condition and whatever problems that we have. But if we can send these particles in a circular path, and if we can continue to increase the speed through as it moves through this particle, so then we can go for very high speeds, no? Isn't it? Right? So then let's say we have a somewhat smaller circular path, right? It doesn't have to go for like around the world or anything, right? So let's say normally the ones we have is about a few kilometers diameter is there, right? So that to reach the necessary speeds and everything. But once it started from here, so then if it continue to increase its speeds, right? So when it reach here, it will be faster, but it does not have to stop here. So then it can continue to move in this path. No? So that means, so then we can reach very close to actually that realistic speed and everything. So they were noted mainly using this kind of circular accelerators, right? Because it can reach very high speed, right? So then to overcome that problem, so then they have developed this kind of technology to use in the magnetic field. Simply, the magnetic fields are used to generate to build up circular paths like this. Understood? Right. Now the most basic circular path is what's shown on the next page, right? Under cyclotron. Okay. Right. So then the first part there in the left hand side of the column it says accelerating particles in cycles. So then that's what we were just discussing before, right? So about the magnetic field. So then I think we did calculations using this formula as well, no? Radius and everything. Okay. Right. So then let's go through that one, the cyclotron part. We'll mention about the magnetic field later. Right. In 1930s, Ernest Lawrence developed the first cyclotron. This was a circular accelerator which could give protons about 1 mega electron volts of energy. In a cyclotron, there are two D-shaped electrodes, right? So the short term for the D-shaped electrons are Ds. D, the shape D, and they were named as Ds. So then, and the particles are accelerated in electrical field in the gap between them. Within the Ds, the particles will travel a long semicolor path because of the magnetic field before being accelerated across the gap again. Then another semicircle, another acceleration across the gap, and so on. So as each acceleration increases the momentum of the particle, the radius of its path within the D increases, and so it steadily spirals outwards until it emerges from an exit hole and hits the target placed in the bombardment chamber in its path, right? Right. So then that's the very first idea, the simplest form of circular accelerator, right? So as it says, we had two electrodes in the shape of a T, right? So then there will be like a magnetic field into this plane, right? I think in the figure it shows, right? So there's a south pole and a north pole. So then in that case it will be upward in the figure, according to the figure, right? So using permanent, they are like permanent magnets, right? So using permanent magnets, right? So they have supplied a magnetic field perpendicular to this D's, right? So then what will happen? So then there's a small gap here. So then this is the path where the particles are traveling, right? So then electrical field is only confined within this region only. So then every time electron passes through this one, here the speed increases. So then it will move through this section, and again when it comes to here, the speed will increase. So then every time it passes through these gaps, that electrical field is causing the speed to be increased, right? So then that last somewhere it says, right? So as each acceleration increases its momentum of the particle, the radius of its path within the D's increases, and so it steadily spirals outwards until it emerges from an exit hole, right? So then these particles, they are not just continuing the same path like this, right? So if it is started from here, so then it is going outward spiral path like this. Why is that? Answer is here. Why it is going outward path, not in the same path? So spiraling outward means what is changing? The radius is increasing. Why the radius increases? This is accelerator. The speed increases, isn't it? So then the speed increases, therefore, so then the radius of the path should be increasing. So as the speed of the path, the radius of the path increases, this is going in an outward spiraling path, right? So then, so as it spiral outward, so then there will be some point where this particle is taken out. So as it comes out of this one, there will be a location where it will be colliding with the particle that we need it to be collided with. So let's place this where what is called as the bombardment chamber. Right? So So that bombardment, the collision happens inside that place, right? Now this everything is calculated, okay? So then you might think, how is that particle is coming out of this place, why it is not colliding from here or something like that, right? So then those things, they are calculated, right? So then suitable suitable mass, suitable electrical field will be supplied so that the particle can exactly coming out from that location only, right? So then it is designed what to come out from there like that, okay, right? Okay, so then that's the basic idea, right? Okay, before we go for the next part, we'll write about this one, right? Circular particle accelerators. Right, like this. When charged particles when charged particles, what's right? Charged particles move through a magnetic field. The path will be curved. Curved due to magnetic forces. You can just sketch a small figure. So write that two equations as well. BQV equals mv squared over r. From that, make the r subject there. Because we will be giving this. So then second, right, in circular magnetic field, in circular particle accelerator, accelerators, magnetic fields are used. particles move in move in a circular path. So then write cyclotron. Cyclotron is a basic. Cyclotron is a basic circular accelerator will just draw like a simplified version of this one. So you just draw those two D's. Basic figure is let's say now. Bombardment chamber. So they mention and you can see that in the figure also it says we are supplying alternating voltage supply to these D's, right? Why? Otherwise, say electron is coming from here, right? So then there should be a negative terminal here. This is positive terminal. So then what will happen? So it will be attracted towards this side, right? But once it comes to this location, if it is the same term, positive and negative values are there. So then what will happen? So then it will be repelled by this one, so it will be slowed down, right? So therefore once it reaches here, so then the positive negative thing has to be changed again, right? So then every time it reaches this point and this point, the positivity and the negative, that the polarity or the voltage has to be switched, right? So therefore again we are supplying an alternating voltage supply there, okay? Right like this. Cyclotron contains two electrodes which is supplied with alternating PD. Next point, as the particles passes through the gap between the D's, passes through a gap between the D's, they will be accelerated by the electric field. As the speed increases, the radius of the path increases. Therefore the particles moving outwards spiraling path spiral path or spiraling path until it emerges from an exit hole where the collision with another particle will occur. The collision with another particle will occur. So we just go through the next part as well. Cyclotron frequency. In order to maintain the acceleration at exactly the correct time, the PD needs to switch direction exactly when the particles exit from 1D to move across the gap between them. This means the voltage supply has to follow a square wave pattern so that it flips polarity instantaneously, and the frequency of these polarity switches only depends on the particle being used and the strength of the magnetic field line. So we know time period equals 2 pi r over v, so that when we discuss in circular motion, right? So then during one complete period of the alternating voltage, the particles will pass through both these, thus completing full circle at the radius that much, right? Then therefore the frequency you can get from that equation. Okay, you don't have to memorize those equations or anything, right? If necessary they will be given, and or else if you want you can work it out as well. So then the frequency needed independent of the radius. This means that constant frequency can be used and the particles will complete each semicircle through the bees in the same time, right? So therefore that frequency of that cyclotron is not depending on the radius, right? So it depends only on the other factors such as the magnetic field supply, the charge and the particle mass, okay? Right, so then that is the basic idea of cyclotron or the circular particle accelerators, right? So then advanced ones we are using now, right? So then about those things we have to discuss next time. So that means the next week is also going to be stories.